This video is on solving equations with radicals, so something like a square root or a cubed root, and rational exponents. So that just means a fraction as your exponent. So our first problem is to solve 2 equals the square root of 4b. So our radical is isolated, so what we want to start with is squaring both sides. That way we can undo the square rooting that's happening. So we want to do that opposite operation. And then we're just left with 4b, so whatever was inside, because we squared a square root. On the left, we get a 4, that's 2 squared, and now we're just solving this old school style, so we divide by 4 and get b equals 1. This next problem has some more going on here, so we have this 9 outside of the radical, so we want to start by getting rid of that 9. So if it's outside, we want to isolate the radical first. So now we've divided the 9 because it was being multiplied. We're left with still that cubed root of 25x, and on the left we got a 10. From here we have this cubed root isolated, so we want to undo that by cubing both sides. So then we get 1,000 on the left, and then the cubed root being cubed undoes that operation. We're again just left with the inside here. So lastly we want to divide both sides by 25 in order to get the x by itself, and we'll get x equals 40, because 1,000 divided by 25 is 40. This next problem, we have those rational exponents, so that means a fraction as your exponent. So remember, one big thing is to think about the rational exponent as a root, right? So this is really the 4th root of y to the 5th. So what we could do is in 2 steps raise it to the 4th power and take the 5th root, but that's going to be a lot slower. What we really want to do first is think about how we can make this into a y to the 1st power. So what can we do to that y to the 5/4 so that it becomes y to the 1st? And the answer is we're going to raise it to the reciprocal power. So the reciprocal is you flip that fraction over. When we raise it to this power, the power-to-power property of exponents will multiply them, so you'd get 5 times 4 over 4 times 5, which is 20 over 20, which is just 1. So we're raising it to that reciprocal power so that we can sort of cancel out these exponents, just get it down to y, because y to the 1st is really just y. So now we need to think about what this really means over here. So that is really the 5th root of 243 to the 4th. And again, you could think of it as 243 to the 4th under that 5th root. Those are equivalent things right here, but this is going to take a long time to do, to raise that to the 4th and then 5th root it. That's a huge pain. What we'd prefer to do is using our associative property, or kind of the commutative property, we want to do the 5th root of the 243 first. That's just going to be faster, because we know the 5th root of 243 is 3. Now we're looking at y equals 3 to the 4th, which is really just going to be 81. So there's nothing wrong with doing the 4th power, then 5th rooting it. It's just way bigger numbers, and it's easier to make mistakes when you have those huge numbers. Next up, we want to start solving this. Our goal is to isolate the x piece. So let's first add 7 to both sides. We get 2x to that 2/3 power equals 18. And then we do not want to think about this as one piece. This is not in parentheses. So we want to get rid of these, separate them, divide both sides by 2. So we've got to isolate just the x with its exponent first. So that's our first step here. So now we've got x to the 2/3 equals 9. So what we want to do is get rid of this exponent. We want to make it just x to the 1st power. The only way to do that is to raise it, both sides, to the reciprocal power, so to the 3/2. That way these would multiply, they'd become just x to the 1st, and then this becomes the square root of 9 cubed. So remember, the dip is the denominator, so really this dip we don't have to write because the square root is redundant. It's just something we don't need to actually show, but if you want to put it there, that's totally fine. So we have the square root of 9 to the 3rd power. Again, there's nothing wrong with cubing the 9 and then square rooting it, but I like to do the square root first, call that a 3 to the 3rd power, and x on the left. Now here's the thing that a lot of people miss, and I missed it this first time too. When you take the square root, you have got to put the plus or minus. So think way back when we did square roots, whenever you take the square root, because we inserted that, we put this 3/2 exponent there. Because we put that there, we have to plus or minus it. There are two options here. So since there are two options, we've got to write them both out. We could have positive 3 cubed, or we could have negative 3 cubed, which means we have two answers, positive 27 or negative 27. Our next problem, and our last problem, has something that we're going to see called extraneous solutions. So first we want to think, okay, I have this square root here. I don't want to look at a square root, so let's square both sides. But notice how I put that right side in parentheses? That is super duper important, because when we square this whole binomial here, it's going to be a little bit more complicated than our past problems. On the left, I'm squaring a whole square root, so the square root cancels out with the squaring process. You're not going to get like a 4 and a 49 here. We're just undoing the square root that was already there, so we're left with the inside as it was. Now x minus 3 squared on the right is really x minus 3 times x minus 3. So we're going to have to FOIL that whole thing out. So if we do that process, we get x squared minus 3x plus 9. If you can do that in fewer steps, be my guest. So now we want to sort of combine like terms, probably move all of this stuff over here. So that means if I'm going to add my 7 and subtract the 2x, and then combine all of these together, we'll be left with a 0 on the left. We got an x squared minus 8x when we combine all of these, and then a plus 16 when we combine the constants. Now we have a quadratic equation, and we spent forever and a half on quadratic equations. The first thing I would try is factoring it. So we want to think, if we're going to factor, there's no number in front, just a 1 there. What can multiply to be 16 and add to be negative 8? So that's going to be a negative 4 and a negative 4, which makes this x minus 4 and x minus 4. So we would set each of these equal to 0, and it's the same thing, so really you don't have to do it twice. And you would add 4, get x equals 4, 2 times. Now what we always want to check for is something called extraneous solutions. We always need to see if there was sort of this false positive that's going on. If we were to plug our answer back into the original problem, is it actually a true statement? So our original problem is right down here, and then we want to check if when we plug in 4 for x every time we see x, is it actually accurate? So we've plugged in the 4, that's going to give us the square root of 8 minus 7 is 4 minus 3. The square root of 1 is 1. Is the square root of 1 actually 1? Yes, it is. So this is our only answer. Sometimes when we do problems like this, we might get two answers, and one of them could be right and one of them could be extraneous. So what would happen is you could get two answers, but actually one of them doesn't work and the other one's the only answer. And the reason this happens is because we did this squaring process right at the top, and we squared with a variable, and that can give you that sort of false positive. So the main thing to just think about is always checking your answers when you have time. But that's it for this video.